India is building its first high-speed railway connecting Mumbai and Ahmedabad. This mega project has a total length of 508 kilometers, an investment of $15 billion, and fully utilizes Japan's Shinkansen train technology to reach an operating speed of 320 kilometers per hour. However, the entire progress of this massive project is being challenged by the most complex technical package C2. This is a 21-kilometer underground tunnel complex, including a 7-kilometer section going straight through the strata beneath the seabed of Thane Creek. To access the construction site, engineers must dig deep vertical shafts tens of meters into the land to lower a 13.6-meter diameter tunnel boring machine. As this machine advances towards the sea, it faces a harsh mechanical problem. At a depth of 70 meters, the cutting disc system not only has to work continuously to break hard basalt rock layers, but the entire equipment must also withstand extreme pressure from the seawater column above. So, how is this giant machine operated to simultaneously drill through the seabed and completely prevent the risk of water flooding into the tunnel system? We will find out right now. Before we start, don't forget to like and hype up this video. And now, let's get started. The 508-kilometer Mumbai to Ahmedabad high-speed railway has up to 460 kilometers designed as elevated viaducts. Using a viaduct structure helps the project avoid ground traffic intersections and limits land acquisition. However, as the route enters the Thane Creek area bordering the economic center of Mumbai, building a bridge over the water faces many obstacles. Therefore, engineers are forced to take the railway track underground through package C2. This underground tunnel complex is 21 kilometers long, starting from the Bandra Kurla Complex underground station. The choke point of the entire project lies in the 7-kilometer section cutting through the seabed of Thane Creek. Geological surveys show that the environment under the creek is an uneven physical mix. The construction equipment will have to pass through zones of soft mud, clay, and especially layers of volcanic basalt rock with extremely high compressive strength. The sudden change in the hardness of the strata, combined with a depth of up to -70 meters below sea level, creates a very harsh construction environment. Access space is also completely limited because the terrain on both sides of the creek does not allow opening horizontal tunnel entrances like typical mountain tunneling projects. To make this underground tunnel section a reality, the actual construction process is divided into strictly sequential mechanical stages. To overcome terrain limits, the first job on the construction site is to dig giant vertical shafts ranging from 39 to 114 meters deep straight down from the land. When the shaft space is complete, the 13.6-meter diameter TBM is transported to the site in separate modules. A super heavy crane system is mobilized to lower each equipment block, weighing hundreds of tons, to the bottom of the shaft. The assembly of this giant machine takes place directly in the narrow underground space. Only when a solid support point is set up at the bottom of the shaft does the TBM officially start its hydraulic system, beginning its horizontal drilling journey straight out to the seabed. When the TBM starts entering the waterlogged strata, this equipment operates on a completely different principle compared to standard mountain tunnel projects. In a mountain environment, the TBM's rotating cutter head simply breaks dry rock. The rock and soil then fall directly into a hopper below and are carried outside by an open conveyor belt system. However, under the seabed of Thane Creek, the excavation face has to deal with massive hydrostatic pressure. This pressure is equivalent to the weight of 35 small cars pressing down at the same time on a surface just 1 square meter wide. If an open mechanism like a mountain TBM is used, the pressure difference would instantly push the entire mass of seawater and soft mud into the tunnel. To eliminate this physical risk, the contractor uses a Slurry Shield TBM design. A pumping station system on the surface will continuously pump liquid bentonite clay slurry to fill a sealed chamber located right behind the cutter head. The pressure of this slurry layer is adjusted by a computer system to generate an outward pushing force, exactly balancing the hydrostatic pressure of the surrounding environment, keeping the ground ahead stable and preventing it from collapsing. When the hydraulic cylinder system creates a pushing force of up to tens of thousands of tons, pressing the machine deep into the strata, hundreds of alloy cutting discs mounted on the rotating cutter head at the front of the TBM will press tightly and roll continuously on the surface of the basalt rock wall. Under this extreme mechanical compression force, the cutting discs directly crush and break the solid rock structure into small fragments. These rock fragments fall straight into the bentonite slurry chamber. At this point, instead of using an open conveyor belt system, a cluster of high-capacity pumps will suck this entire mixture of mud, rock, and slurry into a high-pressure discharge pipe, pumping it back to the surface through the vertical shafts. This closed-loop process ensures that the material cleaning does not reduce the pressure at the drill bit location for even a single second. As soon as the cutter head advances to create space, the robotic erector arm at the rear of the machine immediately lifts the precast concrete segments, weighing several tons and 500 millimeters thick, assembling them with pinpoint accuracy into a new tunnel ring. This ring serves as a solid mechanical abutment for the hydraulic thrust cylinders to push against, generating the force needed to propel the machine forward. To withstand the crushing water pressure at a depth of -70 meters, the edge of each concrete segment is pre-fitted with a specialized rubber gasket system. When the hydraulic cylinders compress the newly formed ring, the gasket is flattened, automatically sealing every mechanical gap. Finally, high-pressure cement grout is pumped into the annular space between the concrete shell and the natural earth wall. This continuous sequence of operations leaves behind a perfectly dry tunnel structure, absolutely isolated from the ocean above. During operation, another extreme technical barrier appears: equipment wear and tear. Continuously crushing solid basalt layers under the seabed will wear down the tungsten carbide alloy cutting discs on the rotating cutter head. When the cutting discs wear out or break, they must be replaced. However, at a depth of 70 meters, engineers cannot pull the TBM backward, nor can they drain water from the excavation face. The only solution is to carry out a high-pressure intervention process. Specialized technicians must crawl through an airlock system built inside the TBM body to reach the cutting chamber at the front. In this narrow space, they must assemble and disassemble mechanical equipment weighing tens of kilograms in a compressed air environment with pressure equivalent to the 70-meter depth of the seabed. This process requires the skills of professional commercial divers. Their working time is strictly limited, and after each shift of replacing the cutting discs, they must spend hours in a decompression chamber to eliminate the risk of bubbles forming in their bloodstream. Successfully constructing the 21-kilometer tunnel complex, especially the 7-kilometer section through the seabed of Thane Creek, plays a crucial role in the operational ability of the entire Mumbai to Ahmedabad high-speed railway. When the final concrete tunnel lining is sealed, it creates a mechanical structure that completely isolates the railway system from the pressure of 70 meters of seawater. This underground tunnel allows the Shinkansen trains to maintain maximum operating speed without being interrupted by ground terrain barriers. When this $15 billion USD megaproject goes into operation, travel time along the 508-kilometer corridor between Mumbai and Ahmedabad will drop from 8 hours to just under 2 hours. This project not only sets a new standard for travel speed in India, but is also a practical proof of applying mechanical engineering solutions to solve physical barriers in a harsh, natural environment. Our technical analysis video ends here. What is your assessment of the Slurry Shield TBM system and the waterproofing solutions in this project? Leave your analytical opinions in the comments below. Don't forget to hit the like button and subscribe to the channel to continue watching the next Megaproject engineering breakdown videos. Goodbye and see you next time.